Okay, why don't we begin the first seminar of 2018? So today's speaker is Joe McInerney, and Joe received his Bachelor of Science degree from University of Missouri, and then his Master of Science from the University of Arizona, both in atmospheric science. And after receiving his MS degree, he began development of algorithms to process and validate data for the Halo E instrument on board the UR satellite at NASA Langley in Virginia, and then he came to Colorado in 1999 as a visitor at NCAR and as a University of Colorado professional research assistant and focused on algorithms to process and validate data for the Hurdles instrument on the Aura satellite. And then in 2007, he came to HAO as an associate scientist and developed enhancements to the CESM and Wacom X model, which is today he will talk about the simulations that he worked on with about the solar eclipse in Wacom X. So, right, Joe.
Okay, thanks, Nick. You guys hear me back there? Okay, good. Okay, so as Nick said, I'm going to talk about using our Wacom X, latest Wacom X model to simulate the eclipse from last year. This project started last year, middle of the year, around the time that Joe Huba and Doug Draub published this paper in GRL where they talked about doing predictions of what would happen in the ionosphere during the eclipse in SAMI 3 model. And then around that same time, I ran into Stan in the hallway, and Stan said, you know, we should do something with Wacom X. We've got a model that's capable of showing something, and at least as a validation effort, we should move ahead and do something with the model related to the eclipse. Not too long after that, Dan Marsh heard about it and said, oh yeah, we're doing this. And so he got things going. Around that time, we found out that Andrew Conley, who's one of the co-authors here, he had already taken the Draub eclipse mask that they used in the study they had done, and he'd actually put it into CAM. So we had a head start. We were ahead of the game before we really got going. And then that led into AGU paper, an AGU abstract, and an AGU presentation last month, and we're working on a GRL paper. So this goes to show you when you bump into somebody in the hallway, something pretty interesting can come out of it. So, and another thing is I spent a lot of time sitting back at the back of the room where a lot of you people are. And so I thought it was time for me to come up here and talk about what I've been doing. I'd never done that before. And it's a lot different standing up here, I'll just say that. Okay, so enough of that. So my co-authors are listed here, but these are the people who helped with this simulation that we did for the eclipse. They help with some of the figures that go into this presentation. But there's a lot of people who worked on Wacom X. And I don't have those people listed here, but those people who know who they are, there's many of them here in the room. And so I thank those people too. So the first obvious question is, what is Wacom X? Many of you already know the answer to this question. Wacom X is a whole atmosphere community climate model extended. It's a comprehensive 3D global numerical atmosphere model of general circulation model. It studies the Earth's atmosphere, the entire Earth's atmosphere from the ground up to 600 kilometers self-consistently. We've got neutral and ion interactive chemistry in the model. Our standard resolution is 1.9 by 2.5 latitude, longitude in the horizontal, and a quarter scale height in the vertical. And because this is based on a climate model, there's a lot of parameterizations in the model, and I've listed some of those there. So before I get into the actual eclipse results, I wanted to go talk a little bit about what I mentioned a little earlier, and that's the development of the Wacom X model, and kind of trace back some of the roots of the developments of the model. And the roots are basically in 3 laboratories here at NCAR, CGD, ACOM, and HAO. So I'll kind of walk through these and talk about how we benefited from a lot of the work that's going on in these 3 laboratories. The first is CGD, and the Climate and Global Dynamics Laboratory. This is a figure I pulled off their website that shows the growth of climate modeling from the 60s all the way up into the 21st century. They started with an Earth system model that basically contained an atmosphere model, a land model, and an ocean model, and that's all they had at the beginning. And now in the 21st century, they have this huge coupled system with a bunch of components, and it's called the Community Earth System Model. The one component of this model that matters the most to Wacom X is this Community Atmosphere Model, and this is a graphic of CAM showing how complex the lower atmosphere is, and just an indication of how much work has gone into this model. And Wacom X relies heavily on this model to be able to do the simulations we do, especially for things that are coming up from the lower atmosphere. But as this model was being developed, people at NCAR and even people in their group started asking, well, what about, at the model top? We have a 50-kilometer model top. What about above that? What about what's going on at our upper boundary? And so that's where ACOM came in. They started developing this whole atmosphere community climate model. They took CAM and they added some middle and upper atmosphere chemistry and physics, and they extended the model up to 120 kilometers. And again, in the development of this model, as things were going along, they started asking a question, well, what about the effects from above? What about getting a model that actually goes up higher, and what kind of things are we missing out on that may be interacting at our upper boundary? So that's where HAO comes in. Ray and Cicely, Art and Ben, and a bunch of other people have been working on model development here at HAO of the upper atmosphere. These are two of the models that have been developed here. They both have an upper boundary of 600 kilometers, TIGCM with a lower boundary of 97, and time GCM with a lower boundary of 30. So they both fit that need that people were seeing to go above 120 and develop a model that extended up even higher. So the only thing missing here was somebody to take this work and incorporate that back into the Wacom model, and that's where Han Lee came along. Han Lee stepped up, leading an effort to take the physics, transport and physics in the TIGCM, and start incorporating that into the Wacom model. And you can see there on the right, he started with Wacom, which has the troposphere from CAM that I showed, that very complex graphic. He has the stratosphere and mesosphere from Wacom with a lot of the chemistry that's in there. He started grabbing pieces out of the TIGCM and getting Wacom X on the right. The middle bullet shows a number of things that were put in the model during this development, and these are things that enabled the extension of the model from the 120 kilometer Wacom top to the 500 kilometer Wacom X. And this is how we ended up with a version 1 of the Wacom X model. This ended up being released, the first release of Wacom X, back in February 2012 as part of the CESM 1.04. So we have this Wacom X version 2 model that we were trying to develop, and we started putting effort in getting the ion transport and electrodynamics from TIGCM into Wacom X. This was a slow-moving project. We had limited resources. There were just a couple of us working on it, and so our results were very slow in coming until Scott McIntosh, leader, he was our fearless leader here in HAO, stepped up with some resources, and we got Ben Foster with his tremendous knowledge of developing the TIGCM involved, along with a bunch of people in HAO, ACOM, and CGD. And the next thing we know, we had this Wacom X version 2 model, much quicker than we would have guessed with the amount of limited resources we had at the beginning. So not only does Wacom X version 2 have the ion transport and electrodynamics from the TIGCM, it also has some improvements to thermosphere dynamics, and these proved to be crucial. The first one there is the species-dependent specific heat and gas constant. We put this into the physics in Wacom X version 1, But we realize it's crucial to have this in the dynamics also, and this really changed things a lot when we put this in. The second thing there is Nick and Hanli especially started playing with this divergence damping, and they noticed when they started monkeying around with this that it was actually improving the tides. The tides had been a kind of a nagging problem, and it was a nagging problem back in Wacom X version 1. It's been a nagging problem in Wacom, and so this was a pretty big breakthrough for Wacom X to be able to get some much more realistic tides. We had hemispheric asymmetries wrong, our magnitudes were off, and this really did improve things. So that was a crucial development, a crucial thing that we kind of stumbled on in the model. We also made some high latitude improvements to the aurora, and then we realized that we could make use of something that CAM and Wacom makes use of. That's this specified dynamics option. Typically, when CAM and Wacom run these long simulations for hundreds of years, they use a free-running model and they couple. And so we typically use that with Wacom X2 when we do our runs. We'll just do a free run and just let the model run and produce whatever it gets for the climate. But there's another option in CAM and Wacom, which is to apply meteorological fields to drive the lower atmosphere. And this can give you a more realistic representation of the atmosphere on a given day. And so this was a lot of work that Chuck Bardeen did to get this stable in the model. And he also made a significant effort to validate the model along the way, and I'll show that in the next slide. So we now have this version of Wacom X2, Wacom X version 2. It's now part of the CESM version 2, and the scheduled release of CESM version 2 is the spring of this year. So that's coming up here in the next few months. One important thing about Wacom X is it's an open source community model, which means we developed this model for the community to use, and we're hoping the community can feed back to us any improvements they make in the model at the same time. And then Hanli just had his paper accepted, which does a thorough job of describing this version 2 of Wacom X, and you can see that in James. So, as I said, we wanted to do some validation of this. Chuck kind of took the lead in one form of validation we were doing, and that was this. He decided that, and a lot of us knew that one of the ways to test any upper atmosphere model is to throw a storm at it. So he picked the Halloween storm and decided to run for 20 days around the storm and look at the TEC, the electron column density, in the model. And so that's what this animation shows, and it starts off with a background ionosphere just on a typical day, and then you gradually see the ionosphere, the TEC start to increase, and then you'll see over the Americas here in a few days this obvious storm signature in the model, and that's what we were looking for, and that's what we were happy to see, is that we were able to simulate that. And then as time goes on, the ionosphere settles back down into the background state. So this was not only a good validation of this SD mode of running Wacom X, but this was a really good validation of how well we had done with the ionosphere. So we have a model with a reasonable ionosphere. It seems pretty stable, so now it's time to do these eclipse simulations. And I'll describe the eclipse a little bit here. The top is something that we've probably all seen. This is the path of the eclipse last year, 21st of August of last year, starting at 17 UT and going to 20 UT and going across the path of totality, going across the continental US. Everybody probably has some memory of where they were on this day. I was just outside of Jefferson City, Missouri, which is what's on the bottom there. The bottom right is NASA had set up a camera right by the Capitol building in Jefferson City, and that's what that picture is on the right, and that's probably similar to what a lot of places saw, but as any of us know who were in the path of totality, this doesn't do justice to what you actually see when you see the eclipse. So now we have the task of putting in the mask, just as Joe Huba and Doug Drob had done, put that into Wacom X. And like I said, we had a head start from Andrew Conley. He had already done this for CAM, and since Wacom X is built on CAM, a part of our work was already done. And Doug gave us this uniform disk mask, and that's the one that Andrew put into and what he did was he applied the mask to the solar flux input in the radiative transfer in the model. And so he used this uniform disk. But as you can see on the right, and as many people already know, the uniform disk, which is the animation on the left, isn't going to be enough if you're in a part of the atmosphere that's affected by the corona, because the corona is still there. This is a picture from Stan, and you can clearly see that you're going to have to deal with the corona even when you're in totality. And so that's why Doug put in this coronal correction factor, and we use that in the processes in the model where we do the corona had an effect. And so 5 processes that we applied the mask to, as I mentioned, the radiative transfer, Andrew Conley did that work. The molecular oxygen and ozone dissociation, the CO2 near infrared, the photolysis, and then the EUV photolysis. The last 2 are the ones that we applied this coronal correction factor to. So now we've got a model that's capable of simulating the eclipse, and here's the simulations we actually did. We ran the model for 20 days to spin up the model, and then we stopped on August 20th, and we did a restart, and then starting on August 21st, previous to that we'd just been doing hourly output, we started doing 5-minute output, which is every time step in the model. We did 2 simulations. We did a Eclipse simulation where we applied the mask, one or the other mask from Doug, and then we did a baseline simulation with no mask, with nothing in there. And we ran each of those for the eclipse day and 2 days following so we could see what actually happened after the eclipse. What we did is we looked at the difference. So the way we did the analysis was we looked at the differences between the eclipse run and the baseline run. And so I've put eclipse minus baseline in quotes, and you'll see that show up in a number of the slides coming up. So the first thing we look at in the model is we can look at the temperature, and that's what this is. On the left, it's the whole vertical range of the model on the vertical, and then the horizontal is between 14 UT and 24 UT on the day of the eclipse at this location that's over the central US. These are eclipse minus baseline temperature differences, and the left, when you plot the whole atmosphere, it becomes dominated by this large temperature decrease in the thermosphere. So we wanted to know, hey, what's going on in the lower atmosphere? So what we did was we took from surface up to just above 100 kilometers to see what's going on. And here you can see at the very bottom, we've got the cooling near the surface. We've got some stratopause cooling, and then we have a whole bunch of stuff going on up in the mesosphere and the mesopause close to 100 kilometers. So I'm going to kind of walk through different parts of this figure and keep referring back to it. And I'll start with the bottom there, the surface. And so here's a map over the United States. This is at 1900 UT on the day of the eclipse. This is where the eclipse was just going off the southeast coast of the US. And so the arrow's pointed there to where the temperature decrease is due to the eclipse at this time. And we're getting about a 6-degree decrease in the model. This is kind of on the low end compared to what a lot of people observed at the time. But the interesting thing here is we see the cooling back along the path of totality. And so even larger cooling back along that path, which is interesting. So that's the surface. That's what the surface looks like. We can now go and look at this. This is near the stratopause. We can look at this cooling with the same map, same representation over the U.S. Same time when the eclipse was just passing off the southeast coast of the U.S. Again, this is temperature difference between the eclipse and the baseline. And here we get a smaller difference, only about a 2-degree difference up in the stratopause region. But the interesting thing here is that this is actually lagging behind the surface temperature minimum. And so it's interesting that the timing, there's actually a time lag as you go up in the atmosphere here. So that's the stratopause. Now we can take a look at what's going on up here in the mesosphere and the mesopause, and there's a lot of variability up there. So we have an animation that we can show. This is the day of the eclipse. This is temperature differences in the mesopause, and you can see the variability show up during the eclipse. You don't really see the signature of the eclipse, the local signature of the eclipse, but you see a lot of variability. And this is lower atmosphere variability coming up and washing out any local sign that there's an eclipse occurring up in the mesopause region. Another thing you see here is that this variability starts spreading globally, and by 12 hours after the eclipse, which is the end of this animation, you can see that the eclipse effects are actually global. So that's the mesopause temperature. Now, if we go back to the left side and look at this big change in the thermosphere temperature, we did another animation to show this. And so this is about 240 kilometers. This is the same thing. And here you see a more localized temperature decrease along the path of the eclipse. And again, things going 12 hours after the eclipse have spread globally. The interesting thing here is when you see after the eclipse, there's this wave propagating away from the eclipse region. This is something that's been seen in other models. It's been seen in observations, and they call this the bow wave. And so that was good that we were able to pick that up in our simulations. So this is temperature, and one other thing we can look at, because we have the chemistry from Wacom, we can look at what goes on to some chemical species during the eclipse. And here's just one example. This is the changes in ozone during the eclipse. This is at 18 UT when the eclipse is over the central US. And also some changes in atomic oxygen that happen at the same time, around 65 kilometers in the atmosphere. Here we get a 95% increase in ozone and a 75% depletion in atomic oxygen. So if we look at the chemistry that's going on in this region of the atmosphere, we can see that there's two reactions that are at play. There's the top left reaction there that is the destruction of ozone from solar radiation, and then there's the bottom left, which is the production of ozone from molecular and atomic oxygen. During the eclipse, the production drops as the solar radiation drops, but this production continues. So you continue to produce ozone gets higher, and at the expense of atomic oxygen getting lower. And so there's probably many more examples of this kind of chemistry that you can look at during the eclipse, and this is just one of them. So now we can switch over and start looking at the ionosphere. This is electron density at four different representations in the model. In the upper left is the E region, about 110 kilometers. These are electron density differences, the eclipse minus baseline again. This is 1850 UT, that same time where the eclipse is over the center of the US. And in the upper left, you see in the E region, we have this localized large decrease in depletion of electron density. That's because in this region, things are pretty short-lived. So once the eclipse passes through, you get this large depletion, and that's it. But on the upper right, you can see where things are more long-lived. You get an actual depletion in the eclipse region, but then some depletion actually trailing behind along the path of the eclipse. And so the F2 peak around maybe 250 kilometers or so is showing that. Also in this figure, you can see that we've got a little bit of a red showing up at lower latitudes, and I'm going to come back to that a little bit later. On the bottom left is the column density, and it looks pretty close to the F2 peak, which is not surprising because the column is typically controlled by what happens at the peak. In the bottom right, we show the peak of this F2 layer, the height of the peak of the F2 peak, the HMF2. And this is a little harder to interpret because this is not just dependent on the electron density, but it's dependent on the temperature. So there's a lot of stuff going on here that go in to give us this variability. And that's clear because we do not even see much of an effect right where the eclipse is occurring. We see effects away from the eclipse. So there's some effort that needs to go into interpreting this figure. But if we go back up to the upper right and talk about the F2 peak again, we can see that this, as I said, there's this low latitude variability that's occurring during the eclipse. So we wanted to look at that a little further. So we put together an animation, and that's what this is. This is at the F2 peak, the number density, electron number density. And if I can get this to play. You can see that we see the depletion along the eclipse path. You can follow the eclipse pretty easily, but we see things start to happen at lower latitudes. And we see even things happening down into the southern hemisphere. So what we believe is going on here is that as the eclipse passes over the US, we get a temperature decrease. And this temperature decrease causes a perturbation in the wind. This perturbation in the wind propagates to lower latitudes and starts affecting the electrodynamics in the low latitudes. The electrodynamics in the low latitudes are what's responsible for these equatorial anomalies, and you can see the effects in the northern and southern hemisphere right near the equator in the equatorial anomalies. And so another thing you can see here that we also saw in the temperature is when you get toward the end of the day of the eclipse, things have become more global, another indication that eclipse effects are really global. So that's the ionosphere. Now we can start looking at some comparisons that we did. I mentioned the paper that Joe Huba and Doug Drob had done predicting what would happen to the ionosphere during the eclipse. This is some results from that on the left. They looked at 36 degrees latitude, 266 degrees longitude at 306 kilometers, and they compared a time series from 16 UT to 24 UT on the day of the eclipse with the no eclipse in black and the no eclipse in black and the eclipse in red. And they just wanted to see what kind of effect you had during the day. The top is electron density and the bottom is the column density. And on the right is the same representation with the same scale for Wacom X. And we can see the Wacom X gets more of a depletion than the SAMI model does, but we're not too far off. It's pretty close, so the models are comparable in the type of depletion they get during the eclipse in both the column and the electron density. One thing you'll notice here is that the baseline, the actual no eclipse line, is different in SAMI and SAMI 3 and Wacom X. And the reason for that is that SAMI 3 uses an empirical thermosphere in their model, whereas Wacom X has a self-consistent thermosphere in the model. And so we're not surprised that we see some different no eclipse time series in the two models.
Can I ask a question about that, Joe? I don't know how familiar you are with what SAMI 3 was doing here, but are they like taking that empirical thermosphere model and changing its parameters along the path of the eclipse? Do you know?
No. So they don't do any.
So it's IMSIS for the whole period, but not with different radiance or anything like that. Or due to the fact that the systems can eclipse.
I don't know how you would put an eclipse in an instance. I guess there's a way.
Or you could presumably adjust the parameters that would represent the anyway. Okay.
No, if I recall the article correctly, they use the same neutral atmosphere to do simulation. Anybody else remember what they did? I'm pretty sure that the neutral atmosphere is the same, and the ionosphere is different. Whereas in Wacom X, everything's different, but in different ways.
Okay, so we get reasonable agreement with SAMI 3. We also compared to some observations. This is some incoherent scatter radar observations done at Millstone Hill of electron density. This is a time series on the horizontal for the whole day of the eclipse from 0 to 24 UT, and then on the vertical axis we get 100 to 500 kilometers in altitude. The top is the Millstone Hill incoherent scatter radar observations. The middle is a high-resolution run of TIE GCM by Tong and Joho at USTC, and then the bottom is our Wacom X. And you can see that not only do we get the daily variability of the electron density on the day of the eclipse, we both see a bite out during the eclipse time. The interesting thing here is that Millstone Hill's not in the path of totality. I think it was about 70%, 70 to 75% there, and they were still seeing an effect. And Wacom X picked that up. So, in summary, we have this version 2 of Wacom X. This is based on a number of ongoing and heritage modeling efforts. It's a whole atmosphere model, so we use this model to do a surface to space simulation of this eclipse from last year. The eclipse results in the ionosphere and thermosphere show us that not only is there an effect on the thermosphere and ionosphere in the eclipse path and in the eclipse shadow, but it actually becomes global in time. And especially when you look at the equatorial anomaly region, there's a clear effect on the electron density in the F2 region and in the equatorial anomalies. We looked at comparisons of Wacom X with SAMI-3, the TIE GCM, and the incoherent scattered radar observations at Millstone Hill, and we get a good comparison with those. So we feel confident that the Wacom X model is giving us some reasonable results, and this turned out to be a good validation effort of the model. That's it.
Are there observations in the southern hemisphere that show the behavior that you're seeing in Wacom X down there?
I think I heard people say that there are observations. We haven't made an effort to grab those and see how close we are.
Go back to next to the last slide, maybe. Yeah, that one. So, would you say then it looks to me like the Thai GCM is doing in detail a better job at altitude than Wacom X? Any comments on
It is a higher resolution model, so I think this tells us that if we push Wacom X to a higher resolution, because we use the same pretty much the same ionosphere that's in the TIE GCM, that we should be able to get some better.
Which we will do.
Right.
Yeah, I mean, I think the fact that Tom is successful in pushing high GCM to 1 degree or 1.25 tells us we can do the same thing with the O+ module in Wacom X. And I think it's a good example of being able to use the heritage model of the Pathfinder, if that isn't a paradox.
Right.
And is there any analysis ongoing about this, like about a bow wave, about what is generating it or what height in the atmosphere? And
I know our GRL paper is going to be part of a series of papers by people and some people looking at this bow wave phenomenon. So I'm not sure.
Wacom X or
Not using Wacom X, but using some observations, some other modeling efforts. So
There was a whole bunch of fascinating stuff presented at this session at AGU. Most of it data stuff. Only a few model simulations. Ourselves and Joe et al. And then the effort that went in and Tom and Yoho are doing.
and Aaron.
Then so there's been there's a special session at AGU. There's a special section of GRL. But then it seems like, well, there's all of the models and data and all this fascinating stuff. People are seeing small scale waves, Rocky Mountain, Lee waves, all sorts of fascinating stuff. No, seriously, they were digging all sorts of interesting things out of the GPS data, and like you said, some of the far-flung measurements, global effects. There's so much good analysis that could come out of this, but I think so far everybody's been working on their own thing,
Yeah.
and haven't had a chance to do all those comparisons. But when this special section of GRL was published, we could go look at all the great stuff that we recorded observationally and see if we could find it in the model,
Right. Yeah.
or vice versa.
So you showed the effect of the eclipse was global and also went on for quite a long time. I think it was 12 hours after you showed. But how long does it take before it gets back to background levels?
That's a good question because it never really does because of the chaotic nature of the model. once you set the model on a different path, you're always going to get some differences in what you get. But so it's always hard to tell when you look at these animations and you get into the next day and then the day after that. When are you just seeing this chaotic divergence, and when are you seeing the eclipse effects carrying forward? And
So we have to run 20 eclipses now?
that's right. Get an ensemble, and then
It occurred to me when you showed that Mesopause stuff. I wonder how much of that is real.
yeah,
Because that was pretty subtle.
right. That's small. Those are small temperature differences.
And we know that the Mesopause is like that. It doesn't just do what it's told. It goes wandering off
Yeah,
based on what the rest of the atmosphere is doing.
yeah.
So I think the wave structure is pretty clear. So that wave structure, I think, is realistic, at least in the model. That's not divergent. But then later, yeah, I think later if you see more almost random oscillations, then that. And also, to answer your question, maybe it's good to look at the GIE system now. That may have less of an effect on the divergence.
Right, and the high GCM by its nature should not have chaotic divergence to a large degree. And so that's actually a fruitful ground for comparison.
The mix effect are about 6 or 9 hours still there. So
Oh, okay.
that's what we can.
And I'm guessing
Right,
by the
yeah.
next day it was gone.
Yeah. So we haven't really run that long, but we run
2
9 hours
days.
after.
Anyway,
we
maybe
can
it's say
still
a
can see.
day later, whatever, things have settled down again. But in Wacom X, it'll never settle down, no matter what. Right, because
Mhm.
you're now you're on a different planet now. It's a different
Yep,
reality.
that's right.
It's the nature of chaotic divergence.
Right.
So, Joe, for this one, is Wacom X one, is the free one or SD one?
Yeah, I forgot to mention that. We just did free running, but
That's probably good because I saw it in terms of full wave stuff. So there was some observations in the, I think it was the early 1990s something. There were some people using the atmosphere data to look at the sense of actually the gravity waves propagating from the surface, maybe stratosphere up. But the rate study for this event, most studies so far for the Boulder wave based on GPS data, something indicating those are surface-sphere gravity waves generate. So maybe using the free one, you can really identify where the source is. So
Right.
maybe that is
yeah.
Not only that, but I always thought this was a big problem in the way Wacom is built, and Wacom X is built, is instead of having a unified solar module that reaches out and does everything in a unified way, because of the heritage of the thing, the radiative transfer comes in one place, and the photolysis comes in another place, and the heating comes in another place, and the EUV is a whole separate sun, and so you got like 5 different things you got to change when you want to do something like an eclipse, which is a big pain. But it also means that if you want to apply different masks, like one for the visible and one for the extreme ultraviolet, which you did, you can do it because they come in different places.
Right.
Not only that, you now have a mechanism where you can turn on and off different parts of the sun. So you can do these experiments, and some of them have already been done.
Yep.
Where you perturb the EUV and leave the atmosphere alone. Where you perturb the atmosphere with the EUV. And you've done some of that mechanistic stuff, which you see in the publication.
That's right.
But you know, there's so many different permutations. It's not always easy to sort it all out, especially if you have to do 20 instances of every simulation.
So, we didn't get a chance to show it in this talk, but probably mentioned that we did an experiment where we only applied the heating from the eclipse in the stratosphere, troposphere. And in that situation, we saw in the opposite hemisphere changes in the ionosphere just from the run where you change the stratosphere and troposphere of about 50% of the total changes. So in that situation, yes, at Millstone Hill, IGCM may be better, but it won't have any of the effects of the lower atmosphere coming out as bow wave
propagating out from the troposphere into the opposite hemisphere and affecting the bad numbers.
Right.
So it very, very much depends on what but to look at the big picture and the full response, we're still thinking of the lower atmosphere.
Right. And I think, like Stan was saying, in the paper we're gonna get more into that. And yeah, I was going to include a figure, but then I realized I'm still trying to wrap my head around it, so I didn't include. But yeah, that's something to look forward to in the paper, is talking about how we're looking at before, during the eclipse and after the eclipse, and looking at all these processes one at a time in an additive way. Yeah.
More questions? Thanks, Joe.
Okay.